Okay, so here is the theorem that we want to prove, at least partially. And I'm going to start by, or I'm going to do just one of these statements. I'm going to do number 2. So I'm going to show that the sum of functions tends to the sum of the limits. Or a way of saying it, the limit of a sum equals the sum of the limits. Okay? So let's prove that. I want to say two comments. One, intuition is not something you're born with. Okay? Intuition is something you acquire as you move along. So for many people here, things we're doing with epsilon, and we're only doing a bit, are counterintuitive. They find it challenging, and that's okay. That's how I started this course in the very first lecture, by saying it took mankind 200 years after they knew they were doing calculus, but still, for that precise definition to show up, it took some 200 years. Okay? That's okay. It takes time to... For me, this definition is intuitive, but that's because I already have that intuition. Hopefully, you're going to have it too, and hopefully, in not too long a time. Okay? Okay. So, let's prove it. So, proof of 2. So again, I start the usual way. Let epsilon be greater than 0. The difference is that now I don't have specific functions to work with, concrete functions. Now my functions are general. I have a function f, which goes to L. I have a function g, which goes to k. I want to show that f plus g goes to L plus k. But the way I'm going to think about it, the way I'm going to do it, is very, very similar to the concrete examples. Okay? I'm going to look at what I need to prove. What do I need to prove? I need to prove that f of x plus g of x, that's my f now, minus L plus k, that's my limit. I want to prove that this thing in absolute value is less than epsilon. That's the definition of the limit. I want to show that this minus what I claim is the limit is less than epsilon. Do you agree that that's what I want to show? I'm going to start working with it and somehow find what the delta has to be. Okay, so I'm going to rewrite it a bit, and I want to rewrite it so that L and F are close and G and K are close, because that's what I know something about. That's the data of this theorem, that f goes to L and g goes to k. So I'll rewrite it as f of x minus L plus g of x minus k. Does everybody agree to this step? Not very deep. Now I really would like to have f of x minus L in absolute value plus g of x minus k in absolute value. Is that equal to this? No. Right, triangle inequality. So this is less than or equal to f of x minus L plus g of x minus k. Good? So this is just a triangle inequality. Okay. Now let's remember again what we want. We want this entire thing to be less than epsilon. True? So if I can make this less than, say, epsilon over 2, and this less than epsilon over 2, then the whole thing would be less than epsilon. Right? So that's what I'm going to do. I'm going to make it happen. How can I guarantee that just this factor is less than epsilon over 2? Can I guarantee that? Less than epsilon over 2. somebody gave me an epsilon. Can I guarantee that this is less than epsilon over 2? The answer is yes. Why? Because I know I'm given that f goes to L, that L is the limit of f, right? So note that the definition, there are two ways of looking at it. If you know a limit exists, then you know that the statement of the definition holds. If you want to prove that a limit exists, you need to prove that the statement of the definition holds. In this example, in this proof, I'm using both. I'm proving the statement of the definition for f plus g, and I'm allowed to use the statement of the definition for f on its own and for g on its own. So I can guarantee that this is less than epsilon over 2. Let me write that. So there exists a delta, let's call it delta 1. There exists a delta 1 such that if x minus a is less than delta 1 and greater than 0, then f of x minus L is less than epsilon. Does everybody agree that this is true? Yeah. That's the statement of the definition for f, and we know that f goes to L, right? Do you agree that the statement of the definition was telling me even more? It said that for any epsilon there exists a delta to satisfy this, right? Right? Yeah. So if epsilon was 1, would there be a delta to satisfy this? Yeah. Yeah. If epsilon was 7.23, would there be a delta to satisfy this? Yeah. If epsilon was whatever this epsilon is divided by 2, would there be a delta to satisfy this? Yeah. So I can write that this is less than epsilon over 2. There exists a delta such that this holds for epsilon over 2. Because it holds for any epsilon I can find a delta to make it hold. Okay? Similarly, so that's for this one. Similarly, let's use a different color. There exists a delta, call it delta 2, such that if x minus a is less than delta 2 and greater than 0, then f of x then g of x minus k is less than epsilon over 2. This holds, what I wrote here in orange holds, because I know that g goes to k. So for any epsilon, in particular epsilon over 2, there's a delta which guarantees it. The definition will hold. So altogether, so here's the last step, I go back up here. I know there exists a delta 1 that satisfies this. I know there exists a delta 2 that satisfies that. Take delta to be the minimal of delta 1 and delta 2, where delta 1 and delta 2 as below. This is not good English, but what I mean is that delta 1 is precisely the delta 1 that satisfies this. Delta 2 is precisely the delta 2 that satisfies this. Okay? No, just those delta 1 and delta 2 that satisfy that this difference is less than epsilon over 2. Yeah. Then, if x minus a is less than delta, if it's less than delta, and delta is the minimum of these two, then it's less than delta 1. If it's less than delta 1, this is less than epsilon over 2. If it's less than delta, delta is the minimal, then it's also less than delta 2. Then g of x minus k is less than epsilon over 2. Put these together, and I get precisely this. So if x satisfies this, then let me color the definition for you. Let epsilon be greater than 0. Take delta to be whatever, and that was derived for all these inner calculations. Then, if x minus a is less than delta, then what we wanted to prove is less than epsilon. So here we did in the same proof, we used the definition, we used our knowledge that the definition holds in order to make statements, and using those statements in order to show that the definition holds for something new. Okay? Again, the first time you see these things, I can see the wheels spinning. Okay? It takes time. Okay? You have to read it again. Think about it. Think what happened here. And if you still feel confused, and I know many of you do, although some of you are asking questions that indicate that they're moving on, that they got it. But if you're still feeling confused, read it again. Think a bit some more. Come and ask again. Okay? Okay, so this is an example of a proof of one of these statements. Okay, so ultimately, remember what our ultimate goal is. So our ultimate goal is to show that whenever you have an elementary function, an elementary function is one of the 8 families, or something that was derived from it via the operations. Remember? Everybody remember what an elementary function is? Say yes. Yes. Okay. Then the limit is obtained by just plugging in the value. Okay? So I want to show you, because some people got concerned here that everything they knew about limits is kind of, hey, well, we learned limits, we know how to calculate limits, what's going on suddenly? So I want to show you example. Let's take a limit and see that what we're actually doing there is that theorem. Okay, so suppose you want to calculate the limit as x goes to 0 of arc tan of 2 cosine x divided by 3x plus 4. All of this to the power 1/2. So there are some more parentheses here. Okay, we want to calculate this limit. Scary? Nah. Oh, we can handle this. How? Well, what does cosine x, what is the limit of cosine x as x goes to 0? 1. Does everybody know that? Okay. How do you know it? You know what cosine x looks like. Okay. Does everybody have cosine x in mind? Right? And at 0, it approaches 1. Does everybody understand what I'm doing with my hands? Okay. So the limit of the numerator in this fraction is 1. What does x go to as x goes to 0? 0. So what does 3x go to as x goes to 0? 0. Why? Why is that true? Right. Exactly. We're using here part 1 of this theorem. I know this is trivial, but I'm trying to show you that this is what's hidden there. That's what's in the background. If our function is x now, x goes to 0, so 3 times x goes to 3 times 0, which is 0. Right? 3x plus 4 goes to 3 times 0 plus 4, which is 4. Do you see that? Do you see that there's limit arithmetics going on there? So back to this board. Cosine x goes to 1. 3x plus 4 goes to 4. Does everybody agree? So what does the quotient go to? 1 over 4. Right? Do you see that that's part 4 of that limit arithmetic theorem? And it holds because the bottom doesn't go to 0. Do you see that? Okay, so this goes to 1/4. What about when I take a square root of it? Okay, so that's not exactly part of that limit arithmetics, but we proved it separately. Remember, we proved that square root of something goes to square root of... We proved that root x goes to root a. We proved it today. That was the first example we did today, right? So root of this thing, if this thing goes to 1/4, then the root of it goes to the root of 1/4, which is 1/2. And 2 times something that goes to 1/2 goes to 2 times 1/2, which is 1. And note that I know that you know that 2 times 1/2 is 1. That's not the point. The point is that if something goes to 1/2, then 2 times the something goes to 2 times 1/2. Okay? Do you see that there's plenty of arithmetics hidden here? Of arithmetics at the limit. Yes? Okay. And finally, arctan of something that goes to 1 goes to arctan of 1, which is pi over 4. So everything you knew is still valid, but what's hidden here is that limit arithmetics. There's one thing that doesn't appear in that limit arithmetic theorem, and that's that we did compositions here as well. We did arctan of something where the something goes to a limit, and that's not a part of that limit arithmetics theorem. Okay? So, and the reason is that in general, there is no theorem that says something of the form the limit of a composition is a composition of the limits, or something like that. That's not true in general. We need something more in order to make it true, and that something is continuity, and we'll get to that. Okay? So there's no theorem of the form limit arithmetics for composition. It's just not true. One can come up with counterexamples, and maybe you'll do that in the tutorial. Yes? You won't be dividing by 0 because you're looking at the limit as... The question was, what if we take the cosine x on the bottom? Okay? So as x approaches 0, cosine of x approaches 1. Okay? So it's true that cosine can be 0, but not where you're looking. Okay? So if it goes to 1, then in a neighborhood, it will always be positive. Okay? So you're safe. But if you would take sine x in the denominator, for example, fatal error termination, you need to do something completely different. Okay? Can't do it using just those theorems. Can't. Wrong. Can't do it. Okay? Yes?
Can the limit be pi over 4, or do we have to set pi over 4 plus 5k?
No. That's precisely the limit. This is precisely the answer. We just argued it, calculated it. Okay? Remember, the limit is unique. There can't be more than one limit. That's the value. This is a value on the y-axis that this function approaches as x approaches 0. Okay? Okay. So what I want to do now is add some more theorems that help us calculate limits. And some of these may be already new to you. Okay? New. Even if you've learned limits before. Some of these you may have not met before. And all of these are useful for the situation where limit arithmetics doesn't hold. Usually when we have limit arithmetics, that's the easiest thing to use. When we can just plug in values, that's the easiest thing to do. But we'll see many examples in which we can't. And then we use all these various tools that we're going to meet now. So the first one is, The first one is, so more theorems. Yes? How would I prove this? Well, proving this by definition is a pain in the eat. You don't want to do that unless you really like to torture yourself. What we do is we prove limit arithmetics. We didn't prove it all. We proved just one of the statements, but you can prove all of them. And eventually you prove the theorem that for any function which is elementary in its domain, you obtain the limit by just plugging in the value. And that's what we really did here. Okay? And then you don't need to prove every single one by hand, by using just bare hands in the definition of the limit. You have a theorem. That's what you do. Okay? I wouldn't even, oh my God, trying to tackle this with epsilon delta might be very painful. Maybe, I don't know, maybe one can work it out, but not fun. I mean, I don't know what, different people have different meanings for the word fun, but I wouldn't do it that way. Okay, so more theorems. One, if f of x, maybe I'll write it down here so we have a full line. So if f of x goes to 0 as x goes to a, then, or in this case it's even if and only if, f of x in absolute value goes to 0 as x goes to a. Okay, so a function goes to 0 if and only if the function in absolute value goes to 0. We're not going to prove all these statements, but I do want you to picture them. Try to picture it in your mind. Okay, let's try doing it together. What does it mean that a function goes to 0? That 0 is the limit. It means, here's a quick, sketchy drawing. At some point, here's the point A maybe. It means that at the point A, the limit is 0. So the picture should be something like, I don't know, something like this maybe. Well, do you agree that this is the picture? This is f. I have no idea what f looks like. Just drew some f. But when x's get closer and closer to a, the values of f get closer and closer to 0. Do you agree that this is a picture to go along with this statement? Yes? Now, this side, the right-hand side here is saying, okay, take the function in absolute value. I'm going to draw it in orange. So whenever it was positive, it's the same thing. Whenever it was negative, it flips, right? So this is the function in absolute value. Do you agree that this orange is the absolute value of f? Yes? And what would be the limit at a? It would still be 0. If as x's got closer and closer to a, the values got closer and closer to 0, in absolute value it would still happen, and vice versa. Do you agree? So that's the idea of this theorem number 1. And I want to squeeze in number 2 on the same board so we can use the same drawing. So number 2 is, if f of x goes to any value, L, then f of x in absolute value goes to L in absolute value. So let's look at this drawing. Let's look at different points now. So this original point we had here was a point where the function went to 0. Let's take a point. Well, if everything is positive, it's boring, right? Because f of x and absolute value are the same thing, and L and absolute value are the same thing, if everything is positive. So let's look at a point where things are negative. For example, this point. Let's take this point to be A now. So f itself was this blue chunk, was this blue line, and when x approaches A, f of x approaches this value here. So this was L. Do you agree? So f of x in absolute value now approaches L in absolute value. Do you agree to this statement? Okay. What is not true, what is no longer true, is the other direction. So for number 2, it's not an if and only if statement. It's only a one-directional statement. If the function has a limit, put in absolute value, it would still hold. But if you take a function in absolute value and have a limit, that does not guarantee that when you throw away the absolute value, it still has a limit. Can somebody come up with an example? A counterexample to the other direction, to convince us that the other direction is false. Yes?
Something like when we have in the denominator absolute value of x minus 2, for example.
Don't give me a formula, because that's hard to translate. Tell me what we want to see in the picture. What should I draw that would convince us automatically that the counter direction, the other direction, is not true? Yes?
L being positive.
The L being?
Positive.
Well, if the L is positive... Hmm?
If the L is negative.
Well, here the L was negative.
No, I meant the absolute, not L, the L on that side being positive. Not the L.
Let's erase this. Okay, wait, let's clear some space for this.
F of x is approaching a positive L.
X cubed.
If f of x approaches a positive L, if f of x approaches a positive L, then in absolute value, nothing's going to change.
If f of x is a negative L, but in absolute value becomes positive.
But that's exactly the situation here. If you're going to look at this picture, you're never going to find a counterexample, because this picture has limits at every point. You should think of a picture where somehow the function does not have a limit. You're looking for a counterexample. So you want here there not to be a limit, and we've seen 5 examples of situations where there's no limit, but in absolute value it does have a limit. Yes?
The Dirichlet function, but instead of being 1 for the rational and 0 for the rational, 1 for the rational and minus 1 for the irrational.
Amazing. Very good. Very good. So, remark, the other, I'll write the details of the example that was provided here in a second. The other direction of 2 of this statement is false. Counterexample, when you want to say that a theorem is false, you want to say that a theorem is not a theorem, all you have to do is give one example for which it doesn't hold. If there's one example for which it doesn't hold, it's not a theorem, right? Counterexample, so the suggestion here was take, by the way, this is not the easiest possible counterexample, but it's still a good one. Take the function, a version of the Dirichlet function, which is 1 on the rationals, for example, and -1 on the irrationals. So I'm not even going to write the formula, I'm just going to draw it. Is it clear what this function is? It's 1 on the rationals, -1 on the irrationals. Okay? Does this function satisfy this? What is this function in absolute value? It's just a constant function 1. Right? Do you agree? So at any point, its limit is 1.
It's a line.
Okay, maybe we will add the details. We need more space.
It's a line, right?
So f here, f is the function 1 if x is rational, -1 if x is not rational. It's a version of the Dirichlet function. At any a, f in absolute value tends to 1 as x goes to a, because f in absolute value is just the constant function 1. Do you agree?
It's a line on 1?
Yeah. F in absolute value is just always 1. When it was 1, it remains 1. When it was -1, it becomes 1. Right? So it tends to 1. But, let's not write at any a. Okay, at any a. But, f itself does not have a limit at any a.
So the important thing about this is that at any a. Not exactly about the L, because the L can be...
No. This example is so good that you don't even have to specify a specific point where it would be a counterexample. It's just a counterexample at any point. Okay? At any point, the function the way it is does not have a limit, because at any point, take any neighborhood, any point, A, any neighborhood, you'd have values at 1 and values at -1. They're not close to any L. Okay? But when you take the absolute value, it's just the constant function 1. Another counterexample, maybe a simpler counterexample, okay? A simpler counterexample. Simple example. Take just a function, for example, which is, let's say, so choose a point, A, here's A, and take the function to be -1 here and 1 here. Just like that. So this is a very simple function. It's not Dirichlet-ish. It's just, -1 up to A and 1 from A and onwards. This function doesn't have a limit at A, right? If you approach from the right, you get one thing. If you approach from the left, you get another thing. Do you agree? So it doesn't have a limit at A. However, in absolute value, it's just the function, the constant function 1, and it has a limit at A. Do you agree? Okay? So the other direction for this thing is false, unless L is 0. If L is 0, everything works. That's part 1. Okay. More statements.
In Dirichlet, there are some limits, right?
In?
Dirichlet function.
No, this function, whether it's this or the original Dirichlet with 0 and 1, doesn't have a limit at any point. It's as limitless as a function can ever be. Okay? At any point, take any neighborhood of any point, any neighborhood of any point, you'll have x's with value 1 and x's with value -1. You'll never be able to guarantee being in an epsilon neighborhood of any number.
It's very, very small.
This is a very, very small neighborhood. I don't know what you have in mind, but the scale here is that this A is now 1 over 1,000,000,000,000, and this epsilon, this delta neighborhood I drew is, whoa, it's small. Very small. Still, there are values 1, values negative 1. Good? Or not sure? Okay, you have to think about these things, okay, and, you know, chew them over and over. Think about them over and over. Get used to them, okay, and ask. Of course, ask, okay, and do show up in office hours and ask, and I'll try to help more and more, and it just takes time to get used to these ideas. Okay, next statement. Where were we? There we are. I want to choose something that I'll prove too. Okay, maybe we'll do this. So we need to erase another board. Let's maybe erase this. We will see examples of how we use all these little claims and little theorems as we go along. So in this new list of theorems that we have, this will be number 3. And the statement is the following. So if f of x is greater than or equal to g of x for any x, and the limit of f of x is L as x approaches a, and the limit of g of x is k as x approaches a. So all of this is the data. If. Then, what can we say about L and K?
L is going to be bigger.
Right, then L is greater than or equal to K. So if F approaches some limit, G approaches another limit, and F is always bigger than G, then that phenomenon is going to carry to the limits. Okay, it's sometimes called monotonicity of the limit. Okay, so if the functions are one is bigger than the other, and they both have limits, then the limits are going to satisfy that as well. In particular, remarks. The first remark is, in particular, when g is just the 0 function, so if f is greater than or equal to 0, and it has a limit, then the limit is greater than or equal to 0. So this is just taking k and g to be 0 and applying the previous theorem. Okay? Good? Say yes.
Yes.
Okay, so that was the first remark. The second remark, theorem 3 does not hold if we replace greater than or equal to, where it appears, so here and here, by strictly greater than, here and here. So if you take, it's easier to look at this particular example to find a counter example. So if you take a function which is always positive, it doesn't guarantee that the limit is always positive.
Non-negative, you're saying, right?
No, I'm saying if you replace the non-negatives by strictly positive, then the theorem is no longer true, is no longer valid. So if you take a function that's non-negative, the limit is going to be non-negative. That is true. That is this theorem or this theorem. But if you take a function that is strictly positive, that does not guarantee that the limit is strictly positive. Can you think of an example?
Root of x.
Hmm?
No.
Can you think of an example of a function that is strictly positive and yet its limit is not strictly positive? What can it be? Can it be negative?
Root of x plus
Wait. Can it be negative? Can L be negative? No, because if the function is strictly positive, in particular it's non-negative, and L has to be non-negative. Right. Very good. E to the x. Well, e to the x at 0 goes to 1, which is strictly positive. But your example was good. So, oh, we don't know what goes to infinity is yet. We'll discuss that later. Now we're discussing only finite limits, okay? But somebody said here x squared. X squared, so, but x squared is 0 at 0.
1 over x squared.
1 over x, no, that goes to infinity. That's
root of
not,
x plus 1, it doesn't work?
no. So, okay, so here's an example. Here's an example. Take the function, maybe, x squared. The truth is, so I can modify this to make it correct even for x squared itself. Maybe I should do that. That would make things much more accurate. So, if f of x is greater than or equal to g of x, for every x, I'm not going to write for every x, because I don't care what happens far away. I only care about what happens in a punctured neighborhood of A, right? That's where the definition of the limit lives. So for any x, add here, in a punctured neighborhood of A. Okay? And this limit, blah, blah, blah. So everything else remains the same. So here's an example. This function, x squared, is strictly positive in any punctured neighborhood of A. It's 0 at A, but the definition of the limit doesn't see what happens at the point itself, remember? It can be not defined here. If you want, that's another way to get around this. You can just say it's not defined at 0. But we don't care what the value at 0 is. The point is that this function is always positive, right? However, the limit at 0 is 0. Do you see that? Everybody? Okay, so that's important. And we will see later on several places where theorems stop holding, become invalid, when strict inequality replaces just less than or equal to. Okay, so these are things to be careful about. Okay, good. Okay, I have what? 5 minutes left. Let me prove one of these. Where are you? Here you are. Let me prove one of these, just so we get some flavor, and we'll continue with more of these theorems and more examples next time. So let's prove. Let's prove number 2, for example. Proof of 2. So let me remind you what 2 was. 2 was the statement that if f approaches a limit, then the absolute value of f approaches the absolute value of that limit. Okay? So let epsilon be greater than 0. What do we want to show? We want to show that f of x, this is a bit confusing, so look up here a second. We want to show that f of x in absolute value minus L in absolute value is less than epsilon. Do you agree that's what we want to show? Everybody? Okay? What do we know? We know about f of x minus L. And now we have absolute value of absolute value minus absolute value. Can somebody give me a clue what would be the next and final step of this proof? Right. Right. The other so-called triangle inequality. Okay, when we discussed absolute values, we had a list of properties. One of them, 5 or 6, I don't remember which one, was the triangle inequality. And then we had another one that said precisely that this thing is always less than or equal to this thing. Remember that? You can look back in your notebooks. It was in the first or second lecture. Okay? So this was a general inequality for absolute values. If you have A absolute value minus B absolute value in absolute value, that's less than or equal to A minus B in absolute value. Remember? Okay. And now what? How do we guarantee that this is less than epsilon?
Get a delta.
Hmm?
Get a delta. Delta.
Right. So we know that this is less than epsilon because that's what we're given. This is what we're trying to prove. If f of x goes to L, then this goes to this, right? So take delta that works for the limit f of x goes to L. Right? That delta is going to guarantee that this is less than epsilon. But then this is less than epsilon. Do you agree? So if you want to be completely formal, you can add a line here and say, then if x minus a is less than delta, then this is less than this, and we know that this is less than epsilon. Good? Do you see again that we're simultaneously using the fact that we know the definition for this in order to prove that the definition holds for this? So we're using both directions. Yes?
But isn't that what we always want to show? That exactly what you just pointed out?
Yeah, but now there are two things here. So what we're trying to prove is...
Oh, we're just trying to prove that.
Right.
Oh,
So we want to prove that it holds for this. We know that it holds for this. And luckily enough, there was this magic property of the absolute value that tells us, well, you don't have to work hard. You know it for this. This is smaller. There you go. You have it for free.
so we're using actually the last step of the definition.
We're using the entire definition, the fact that it holds for f of x approaches L, in order to show that it holds for absolute value f of x approaches absolute value L. Good?
Yes.
Okay. So let's stop here for today, and we're going to continue next time with more little theorems like this.